Hello, everybody, and welcome to Introduction to Astronomy. I am your professor, Jim Caffey, and I am absolutely thrilled to kick off our journey together through the cosmos with Module 1. Now, before we can lift off with our study of astronomy and the cosmos, we have to start with the absolute foundations of astronomy and get a proper introduction to the night sky. And since this is a recorded lecture, I highly encourage you to treat this and the other videos and audio stuff we have in the class just like a live class. Grab your notebook, get comfortable, and remember that you have a superpower here. You can pause, rewind, and rewatch me at any time you need to. But wait, there's more. I have stacked this class full of highly engaged content in multiple formats. Nobody really likes reading a boring textbook, right? So, leveraging the power and versatility of Google Gemini AI and Gemini Notebook, I have personally created a number of files, including study guides, podcasts, video explainers, custom slide decks, and interactive infographics. This course is a complete rewrite of my 16-week astronomy course, and it's going to be completely modernized. So join me as we span everything from the mind-boggling scale of the universe right down to the elegant physics that keeps our planets in their orbits. As always, I am Professor Jim Caffey, your personal astronomer. Hey, guys, space is vast, and sometimes it really can feel a little bit intimidating, especially when you're dealing with an online class. But by the end of this lecture, I promise you're going to feel right at home looking up at the stars. Let's go ahead and get started, as we always will, with our learning objectives. And before we dive headfirst into the cosmos, let's look at our roadmap for today. And these are the learning objectives. They are very, very important that we get this in first so that we know where we're kind of going. So I want you to pause the video here if you need to jot these down and continue on. So today we're going to focus on how we use the scientific method to study things that are billions and trillions of miles away. Objects that astronomers like myself can't actually touch or bring into a laboratory, except for those 842 pounds of lunar moon rocks we got from the Apollo missions in the late 1960s and early 70s. We have a little bit of that. But by the time we wrap up this video, you're going to be able to map out your own cosmic address. You'll be able to explain a mind-bending concept about why looking into space is literally looking back in time, decoding the basic movements of the night sky, and understanding the gravity that rules it all. It is a big agenda in a very big universe. But we're going to take it one step at a time. Let's start by zooming out, and I mean way out. If you're sending a letter to maybe an alien pen pal, I don't know, on the other side of the universe, if you write on it, "From Earth with love," that's not quite going to cut it. You need a full cosmic address. So we start on the Earth, which orbits around our star, the sun. This makes up our solar system, the foundations of it. But our sun is just one single, small, average star out of hundreds of billions of stars swirling around in the Milky Way galaxy that we call home. If we zoom out even further, the Milky Way hangs out with a few dozen neighboring galaxies, kind of out there in the cosmic suburbs. And we call that group the local group. I know we have a lot of great names in astronomy. Now, the local group is by itself just a small, tiny branch of the massive Virgo supercluster of galaxies. And even incredibly beyond that, that supercluster is just a tiny fraction of the entire observable universe, which only 5% of have we discovered the mass for. 95% of the universe is hidden to us as dark matter and dark energy. So it's a mind blowing scale, and we are wonderfully small, yet we are a connected part of this massive, beautiful structure of the universe. Now, here is a cosmic rule that sounds like it was pulled straight out of science fiction. Looking out into space means you are literally looking back in time. Why is that? Well, light, as incredibly fast as light is, it still takes time to travel across the massive distances across the universe. Now, in astronomy, we measure these vast distances in light years. But I don't want you to worry about that word year. Don't let that fool you. A light year is a measure of distance, not time. It is a distance of light that travels in a single year. So, how far does a beam of light travel in a year? And we've measured it. We know what it is. We know the speed of light, and it's about 6 trillion miles. That's a light year. That blows everybody's minds away, I think. But because of this speed limit, when you step outside and you look at the sun, you're seeing it as it was 8 minutes ago. If a star out there I'm observing 100 light years away were to just explode right here, right now, today, we would not even know about it for 100 years, a century, because that light has to travel across space to reach our telescopes. So the telescope isn't just a tool for seeing far away, it is literally a time machine. Now, let's add in here, how fast is the speed of light? Well, it's about 186,000 miles per second, or about 300,000 kilometers a second. At that speed, a beam of light can go all the way around the Earth 7 times in just 1 second. Now let's bring things back to home a little bit. When you walk outside tonight and look up, it feels like we're standing under a glass dome over our heads studded with stars. And lucky for all of us, Arizona has some of the best and darkest skies anywhere in the world. And that's why I love observing there so much. I have been to Kip Peak National Observatory, which is south of Tucson, and it's the largest observatory complex in the world. We'll get into some of my observations there throughout the course. But I don't live in Arizona. Where I live in Springfield, Missouri, even the most rural farmland that a university would put an observatory on that I used to work at, even out in the dark places of the county, it would not be as brilliant of a night sky as what you guys have in Arizona, home to more observatories than anywhere else in the world in our own backyard. Now, ancient people believed that this was a literal dome over us. Today, astronomers call this imaginary globe the celestial sphere. And even though we know the stars are all different distances and depths and places, if we simplify things and treat those stars like they are projected on the inside of that sphere, that helps us map them out better and understand them. And so we call these simplified versions models. And there are a few key terms to know here. The point directly above your head, no matter where you are on the ground is your zenith. The zenith is straight overhead wherever you are. Then where the ground meets the sky, that is your horizon. So if you look straight out where the ground and the sky touches, that is your horizon. And then if we take Earth's equator and the north and south poles of the Earth, and we project those out into space, we then get the celestial equator, which divides the sky into two halves, and the celestial poles. So if you were standing right at the North Pole on Earth, you look straight overhead, you will see the North Star. You would see also the North Celestial Pole. If you're on the equator of the Earth and you look straight overhead, you're looking at the celestial equator. And this gives us the ultimate global grid system to track the stars. And humans are hardwired to find patterns. Ancient cultures from all over the globe used to look up and they saw different things in the stars. They saw the outlines of heroes or gods or beasts or whatever it was in the stars, which created the constellations. So in ancient times, there were hundreds, even thousands of constellations, all created by different cultures. Today, modern astronomers like myself, we still use this concept, but it was formalized around the start of 1900 or so. And so in this formal way that we look at the constellations, we have determined there are 88 official constellations in the sky. Keep that number in mind, 88 official constellations. And they divide the entire sky into neat little scientific borders, kind of like the drawing of the states on a map of the United States. Where is your state boundary? Well, constellations have boundaries also. So if we look at the screen there, and that's Orion, my favorite constellation. The stars that you see there that connect the dots of Orion, yes, those are belonging to Orion. But if you have the planet Saturn down there within the blue box, we would say Saturn is also in the constellation of Orion. So anything in that border, that blue border, is part of that constellation. And now at this point, I want to kind of clarify a common misconception. Don't confuse an official constellation with an asterism. An asterism is just a very familiar, recognizable pattern of stars. Fun fact, the Big Dipper, it's not a constellation, guys. The Big Dipper is an asterism, a famous pattern that sits inside the borders of the much larger official constellation, which we call Ursa Major, or the Big Bear. Now, we also track the zodiac in the sky, which these are the constellations that we see across a specific line and a path in the sky. This path appears to be where the planets, the sun, the moon, and all the constellations are going through this line over the course of a year. And we call that the ecliptic. This path in the sky where the sun, the moon, the planets, and where the zodiacal constellations of the zodiac are found. Now, long before we had smartphones or telescopes, civilizations like the Greeks, the Mayans, and the Babylonians, they were meticulous sky watchers. They used the stars as a calendar to predict seasons, plant crops, and navigate the oceans. If you stand outside, everything truly looks like it's revolving around us, right? You don't feel the earth spinning at 1,000 miles an hour. Because of this perfectly reasonable observation, the ancient thinkers like Ptolemy and uh, Hipparchus, they formalized the geocentric model. Geo means earth-centered. So this placed the earth right in the dead center of the universe, and it didn't move. It was made completely by intuition, and it made sense to them at the time, 3,000 years ago. But as astronomers collected more data over the centuries and centuries, trying to explain the weird backward loop that some of the planets like Mars goes through, using an Earth-centered model required some really incredibly messy and frustrating math. And I don't know about you, but I stay away from the messy and frustrating math. So, enter Nicholas Copernicus in the 16th century, and he shook the very foundations of science, philosophy, and religion by suggesting a much cleaner idea, the heliocentric model. Helios means sun. So, he argued that the sun, not the earth, sat at the center, and that we are just one of several planets that orbit around it. This was a massive paradigm shift. It stripped humanity of its center of the universe status, which, as you can probably imagine, sparked a lot of controversy, especially within the church at the time. But from a purely scientific standpoint, putting the sun in the middle made sense to explain the looping movements of the planets and make them beautifully simple. Now, the heliocentric model was a brilliant theory, but science requires solid, undeniable proof. And that proof was built in and designed by a dynamic duo from our astronomy history books. First, we have Tycho Brahe. Some of these folks we call by their first name, Tycho. Some of them we use their last name. But Tycho Brahe was hired to be the royal Danish astronomer to the King of Denmark. And Tycho Brahe was just colorful, he was wealthy, he was a nobleman who really spent decades gathering the most meticulous, highly accurate data on planetary positions that had ever been recorded by the naked eye at the time. Now, I want you to hang with me until the end here because I have a story to tell you about Tycho Brahe. Tycho wasn't a great mathematician, but man, he was a really good observational astronomer. And when Tycho passed away, his brilliant assistant, Johannes Kepler, took 40 years of observations, that mountain of data, and then he used his mathematical genius skills to figure out exactly how the planets were moving. Kepler realized that Copernicus was right about the sun being in the center, but Copernicus had assumed planets moved in perfect circles. Kepler's math proved that they did not. So here's my story about Tycho Brahe. As this goes, Tycho was having dinner with the king of Denmark one night, and the rules were you could not leave the table until the king was done. Well, the king liked to eat a lot. He liked to have his beverages, and he didn't want to get up. Tycho, on the other hand, is sitting at the table. He has had quite a few beverages at the dinner, and Tycho really needs to excuse himself to relieve himself. But the king wasn't done, so Tycho had to stay there. And what happened was explosive. Tycho's bladder ruptured, and he died a couple of days later from the infection. And then Kepler takes over. And there's your story time for today. Now, getting back to the lecture. Kepler, he broke down his groundbreaking findings into three distinct laws. And in science, so many things do come in threes. So, Kepler's first law, it states that planets do not orbit in perfect circles. They travel in ellipses, which you can think of as stretched out circles or ovals, with the sun sitting a bit off center at one specific focus point. Kepler's second law, I call the equal area and equal time law, which I also like to call the pizza law. We all like pizza. If you imagine a planet sweeping out a slice of pizza as it orbits that yellow equal area, imagine it sweeps out that path in the orbit to keep the slices equal in total area. A planet has to change its speed. And when a planet gets closer to the sun in the elliptical orbit, the sun's gravity whips it around faster. And when it swings farther away, it slows down. So planetary speed is not constant. It is always constantly fluctuating. Now, Kepler's third law gives us a pretty beautiful mathematical harmony. And it is written simply as p squared equals a cubed. Go ahead and pause the video here if you need to and write that formula down. I promise this is probably the most math we're going to do in here, but you just see the relationship here. What Kepler's third law means in plain English is that the farther a planet is from the sun, the longer it takes to complete one orbit. And this isn't just because it has a longer, wider path to travel. The math dictates that it is exactly moving physically slower through space. For example, Mercury, the closest planet to the sun, it is so close, it zips around the sun in 88 days. Whereas Neptune, out there in the far reaches of the solar system, moves pretty slow. And it takes a nice, casual 165 Earth years to make one single trip for Neptune. Now, while Kepler was crunching all these incredible numbers, Galileo Galilei in Italy started doing experiments with a brand new invention. Now, here's another misconception. Galileo did not invent the telescope. The telescope, the parts of it, were first created by lens makers in the Netherlands. They did that. They put the lenses together, but it was Galileo in 1609, way back, when he was the first to rigorously point his little bitty telescope at the heavens and record his findings. And this was the first time this has happened. What he saw shattered that old geocentric view for good. He discovered 4 moons orbiting around Jupiter. This is huge because it proved Earth was not the center of all motion. He also observed that the planet Venus goes through phases, sort of like the ones our moon goes through. The only physical way Venus could ever go through those specific phases is if it was orbiting the sun, just like Copernicus predicted. Now, Galileo's telescope took that heliocentric theory out of the realm of abstract math and proved it as physical reality. So, Kepler explained how the planets moved, and Galileo proved they orbited the sun. But it took another guy to explain the why. It took Sir Isaac Newton to explain why this all happens. And Newton changed physics forever with his 3 laws of motion. I know, 3 more laws. So, in his spare time, Newton also just decided to invent calculus and, put pain on all engineering and physics majors in college, including yours truly. Now, Sir Isaac Newton taught us that objects in motion stay in motion. Objects in motion stay in motion unless acted upon by an outside force. That's key. He also gave us the famous equation F equals M times A, where the F is the force and it equals the mass times acceleration. So we can measure force in physics with just the mass and the acceleration. And he also noted that every action has an equal and opposite reaction. Every action has an equal and opposite reaction. The brilliance of Newton was realizing that these rules don't just apply to things on Earth, they govern the entire cosmos. And Newton tied all this together with his law of universal gravitation. And this is a big one. Now, you might see a little bit of math when looking at this in other videos or in the text, but you really don't need to know that math. Newton took his law of universal gravitation and he had this massive realization. The light bulb went off above his head. The exact same invisible force pulling an apple to the ground is the same force that keeps the moon orbiting the Earth and the Earth orbiting the sun. And gravity depends on two main things: the mass of the object and the distance between them. If you want to think of an orbit as like a delicate balancing act, a planet is constantly falling towards the sun due to gravity. But that planet possesses enough sideways speed that the curve of it just falls perfectly into the curve of the sun. It keeps falling around the sun, but it keeps missing the sun because it's going fast enough to stay in orbit. And the result is a perfectly balanced, continuous loop that we do call that orbit. So now let's come back to home a bit and look at how our own planet Earth moves. In astronomy, it's very easy to confuse the terms rotation and revolution. So let's lock them in right now. Earth rotates on its axis like a spinning top every day, all day. The Earth is rotating on its axis. One full rotation takes about 24 hours. And this is what gives us our day and night cycle. It's spinning like a spinning top. At the same time, this spinning Earth is going to orbit or revolve around the sun. So for the planet to move around the sun, that is revolution. Revolution is going around something else. Rotation is spinning on its own axis. Now, we make this cosmic lap every 365.24 days. Not quite a year, a little bit more, but that does give us our year. So you're sitting on a rock that is spinning while simultaneously racing through space. We're moving a lot faster now than it feels like we are, isn't it? So let's use this slide here to debunk one of the most common myths I see with students and really all in science. Many people have the belief that summer happens because Earth gets physically closer to the sun. Well, that is a misconception. That is wrong, completely false. In fact, for us in the northern hemisphere, Earth is actually closest to the sun in January. The true reason for the seasons is the Earth's axial tilt. Our axis is tilted 23.5 degrees, and that's what we spin on. You remember the globes in school and they were tilted, right? As we revolve around the sun, that permanent tilt means that one hemisphere leans in towards the sun while the other leans away. If you think of it like a flashlight, you shine that light straight down, you're going to get a nice concentrated beam of light. Think of that as summer, the direct sunlight. You know how hot it is in summer. Now, if you angle the flashlight and bend that light into a wider area, it spreads out and gets weaker. And that's what we think of as winter. The hemisphere is leaning away and gets shallow, spread out, weak, not powerful sunlight. Here's how you can think about the difference in the distance that we are from the sun during the various seasons. So we usually are around 91 million to 94 million miles away from the sun. And to think about why the misconception exists and how to debunk it, let's imagine we're outside and we have a bonfire going, okay? Bonfire is way over there, and we take one step closer to that bonfire, just one step. Are you going to feel the hotness of the bonfire a lot more? If you take one or two steps back, do you get really cold all of a sudden? No. And that difference is key because it doesn't work the way we think it works. You have to think about where the sun angle is concentrated. Next up is our nearest cosmic neighbor, the moon. Now, the moon doesn't create its own light. It just acts like a giant dusty mirror that reflects sunlight. And as the moon revolves around the Earth, we see different amounts of sunlight up there from our perspective. We see different amounts of the lit side of the moon, and that creates the beautiful phases of the moon. And we're going to be doing a really major project on the phases of the moon starting next week in Module 2. Have you ever noticed how we always see the same side of the moon, that man in the moon face? Why do we always see those features? Well, that is because this fascinating gravitational effect going on called synchronous rotation. And over billions of years, Earth's gravity locked the moon into a rhythm. The moon rotates on its own axis at about the same speed that it orbits the Earth. This takes roughly 27.3 days to happen. About a month. About a month. Now, coming up in Module 2, I'm going to assign this major project. And we'll be observing the phases of the moon. It is a long-term project designed to get you outside and make observations. After these 8 weeks, you will never look at the moon the same again. That relationship between the Earth and the moon is a literal gravitational dance, and we see it play out daily in our ocean tides. Now, I realize most of us don't live near the ocean, but it's still important to note these concepts. We see this in our ocean tides. The moon's gravity actually pulls on the Earth's oceans, and this creates a bulge of water on the side facing the moon. And then a secondary bulge forms on the far side. And as our Earth rotates on its axis throughout those watery bulges every day, coastlines will experience high tides and low tides. Now, when the sun, the moon, and the Earth are all perfectly lined up in a straight line, which does happen twice a month during new and full moon, the gravity combines forces to create really dramatic, really extreme tides that we call spring tides. Opposite of that, when the moon is at a 90-degree angle, right angle to the sun, their gravitational pulls fight each other. And that results in much milder, much weaker tides that we call neap tides. Boy, we've made it through a good chunk of lecture. And if you want to pause the video, get up, stretch your legs, get a drink, do so. Because we're going to start summarizing Module 1 here. We have covered an immense amount of ground in Module 1 today, journeying from the farthest reaches of the observable universe right back down to our own oceans. Let's take a look at what we've covered and recap our core foundations. Our universe is organized into a massive cosmic hierarchy because light speed is finite. We learned that the mind-bending reality of looking deeper into space actually means we're looking back in time, seeing stars that were there thousands of years ago and not now. We learned how to navigate our night sky using the celestial sphere a bit and turning a chaotic dome of stars into a readable map. And that's going to be key in our lab this week. We traced astronomy's dramatic, centuries long evolution, shifting from Ptolemy's intuitive model of Earth centered view of the cosmos to the revolutionary sun centered breakthroughs of Copernicus, Galileo, Tycho, and Kepler. We looked at how Kepler mapped out the elliptical paths and orbits of the planets and how Sir Isaac Newton provided that universal gravity-based physics to explain exactly why those orbits even exist. And finally, we brought it home to prove that the Earth's seasons are caused entirely by that 23.5-degree axial tilt. And we learned that the lunar phases and the ocean tides are a direct product of our dynamic gravitational relationship with the moon. Now, to officially wrap up our lecture, I have created and provided this comprehensive infographic. You'll definitely want to check this out in the slide deck. This slide is your ultimate visual cheat sheet for everything that we have covered today, and I highly recommend taking a copy of this. So let's do a quick, exhaustive walkthrough of these visuals to cement these concepts. On the left, if you direct your attention to the top left, you'll see our cosmic zip code. We start small at the Earth, moving out to the solar system, the Milky Way galaxy, the local group of cluster of galaxies, on out to the massive Virgo supercluster that's about 50 million light years away, and even the boundary of the observable universe, which we think to be about 13.8 billion light years away. This beautifully illustrates that mind-spinning hierarchy we discussed earlier. Beneath that is the great debate. Notice the visual contrast here. On the left, wrapped in classic parchment, is Ptolemy's geocentric model, which was intuitive but was incorrect, placing a stationary Earth at the center of everything. On the right, in modern deep space blue there, we have the heliocentric model that was pioneered by Copernicus. And then right below that is the smoking gun, Galileo's telescope, which provided that hard physical evidence, like the phases of Venus and Jupiter's moons being discovered, to finally prove the sun is at the center. Now, if we move over to the right side and focus on the physics keeping all of this together, in the top left of that section on the right, we have an illustration of Kepler's 3 laws. And you can clearly see that the orbits are not perfect circles. Rather, they're ellipses. And the graphic here shows that a planet actually speeds up as it gets closer to the sun's gravitational pull. And right next to that is Newton's universal law of gravity. I love this visual. I really do, because it shows an invisible tether connecting both an apple falling to Earth and the moon orbiting our planet. It's the same exact fundamental force. And below that physics section, we tackle our local Earth-Moon dynamics. You'll see a great visualization on the reason for the seasons, explicitly showing that 23.5-degree tilt of the Earth's axis. We notice how the sunlight hits directly in the summer and at a much shallower angle in the winter. Next to that is the lunar phase diagram, perfectly tracking the monthly cycle of the 8 phases from new moon through full moon and back again to new moon. And finally, in that bottom right corner, we have just a small data table for the inner terrestrial rocky planets like Earth, Mars, Venus, Mercury. If you look closely at the period column, you can see Kepler's third law in action. The further the planet is from the sun, the longer its orbital period. Take a screenshot of this or download it from Canvas and use it to kind of dominate your assignments coming up. And you're now officially ready to move on to other parts of the course. The first lab is called Smartphone Astronomy 1, and we'll go into the discussion board. Let's carry this momentum forward, and I'll see you under the stars. To wrap things up and get us interacting with each other, we head over to the discussion board. And I'm going to give you a prompt, and you can kind of decide which part of the prompt you want to do. So on the Canvas discussion board for Module 1, here's the prompt for the week. Reflecting on our cosmic address and the concept of light travel as a time machine, how does realizing that you are looking at the ancient past, how does that alter your perspective when you look up at the night sky? Then choose one historical astronomer that we discussed today, such as Galileo, Kepler, Newton, Tycho, and explain how their specific breakthroughs fundamentally altered humanity's place in the universe. Make sure to post your initial thoughts by Friday night at midnight. And then by Sunday, at the end of the week, you need to reply to at least 2 of your classmates, giving them some of your insight on their discussion post. This is the heart of the class, where we act like we are a class together in a classroom, and we are there to discuss the topic all together. It's just set up in a way that you don't have to be on the same time as somebody else. You're going to give your feedback, constructive and whatnot, to those students, just as if we were in a real classroom having a 2-hour-long discussion about the universe. I can't wait to read your insights and jump into this conversation with you guys, and I'll guide you the whole way. As always, I am Professor Jim Caffey, your personal astronomer. Thanks for watching, and I will see you all next time under the stars.